So I have implemented this technique in this library called HeapLib, and it exposes a number of different functions for manipulating the heap. The two most important ones are alloc and free. They implement the plunger technique, so you don't have to worry about any of this. You can just call alloc some size, and you'll get a block of that size, and then you can free it. All of the plunger stuff is just handled internally. The library supports Internet Explorer. I've tested it on 5, 6, and 7. The way I uses the heap hasn't really changed much between these versions, so the same code just worked. It's an object-oriented API, so you create a class and you have a number of functions that you can call. It has some cool functions for logging all allocations on the heap and also outputting debugging messages. I will show you how this works. You have to have the WinDBG debugger attached to Internet Explorer, and then you can get debugging information about exactly what blocks are being allocated and where. So that's very useful for making sure that your understanding of how the application uses the heap is actually correct. You can also see the result of your actions on the heap. You can see the result of your code. We have the functions, as I already mentioned, we have the functions for allocating and freeing blocks of arbitrary sizes and contents. This is the most important part of the library. And we also have a couple of functions. They're the more high-level functions for heap manipulation. For example, we have functions for freeing the look-aside for blocks of a particular size. We have functions for freeing chunks to the look-aside or to the free list. Unfortunately, the high-level functions don't work on Vista because Vista uses, and also IE7 on XP, because it uses the low fragmentation heap, which doesn't have a look-aside. So those particular functions are specific to the heap implementation. But even on Vista, you can still use your basic building blocks, the alloc and the free function. So once somebody with more free time than me goes and reverses the Vista heap, the low frag heap, and figures out how it needs to be manipulated and tweaked, you can just write a new high-level manipulation function using the lower-level ones, and then you can plug it into this library. So here's some sample code for how to use the library. First, we import our library with a script tag. It is called heaplib.js. It's a very imaginative name. Then we're going to create a new heap object, which is an instance of the heaplib.ie class. And the .ie is there because I was going to implement the same techniques for other browsers too. I haven't gotten around to doing it yet, but if somebody wants to play with it, feel free to send me a patch. Then we're going to call the garbage collection function GC, which calls the garbage collector, and it also flushes the OLE cache of free blocks. So after we've called the GC function, we've ensured that the heap is in a clean state, and we're ready to manipulate it. Then we'll turn on heap debugging, and we will allocate 2 blocks using the heap alloc function. The first argument of that function is either a size or a specific string. If you pass a size, then the library will allocate a block of that size, and it will fill it with just basically A characters. If you pass a specific string, then the function is pretty much equivalent to strdup. So you're going to allocate a block of the same size and fill it with this data. So this is the method we use to put specific blocks of shell codes or vtables or something else on the heap. The second argument to the alloc function is a tag. In this case, we use foo. You can use any number of tags for different allocations. And the tag identifies the specific block that you've allocated there. When you call the free function, you pass it a tag, and the free function will free all the blocks that have been tagged with that particular tag. So you can use this to allocate 3 blocks and then free the one in the middle, because you're just going to give the one in the middle a unique tag, and then you can refer to that particular allocation. And finally, we'll turn off debugging. I will do a little demonstration of how this works. I have a VM here, Windows XP. Here's the JavaScript code for heaplib. Here's this HTML file that uses it. And here's the actual code that will get executed. The code is identical to what I just showed on the slide. But before we run it, I'm going to attach the debugger to Internet Explorer. And the communication between our heap library and the debugger happens through a number of conditional breakpoints, which I've repurposed some of the ATAN and ASIN and ACOS functions in JavaScript. And if you have a special magic value as the first argument, that the conditional breakpoints will output special debugging information. You can read the paper for more details like that. I also have 2 breakpoints on RTL allocate heap and RTL free heap, which will be used to print out the results of all allocations and frees. So I'm going to let Internet Explorer run, and make this smaller. Yeah. I'm going to run the code, and if you look at the debugging output here in WinDBG, you see that we started by flushing the cache, running the garbage collector, flushing the cache again just to be sure, and we enabled heap breakpoints. After we enable the heap breakpoints, we'll see a trace of all allocations that IE does. Here we allocated the first block, which is 512 bytes, and this is the address that we got. This is the address of the block. Then we allocated a 16-byte block. This is the BBBBB allocation. The 16-byte block was allocated at this address. Then, when we called the free function here, it deleted the references to these 2 blocks, and then it flushed the OLE out 32 cache. And during the flushing, the 2 blocks that we had just allocated were freed. So this is how to use the library. Yes?
What's the log for the first allocation? You have 3 allocations.
No, I have 2.
What about
Oh, sorry. Let's look at the source. Yeah, that's just a spurious line. In the actual source, I only have 2 allocations. So, sorry about that. You think after I've given this presentation a couple of times, I would have my demo at least working right, but all right. Oh, and by the way, feel free to ask any questions at any time. So you can interrupt me if you want me to elaborate on something. So what can we do with this? Here are a few examples of how to manipulate the heap. Now, this you cannot fit even an introduction to the heap and the heap algorithms in a talk, and much less one part of a talk. But I will give a very brief overview to sort of give you a feel for what kind of level of detail is required to actually use this technique. Here's how the heap works. It's pretty much taken from Matt Conover and Odette's presentation from CanSec a couple of years ago. This is the heap before Vista. It's pretty well understood at this point. The heap allocator manages memory in blocks, and each block can be either free or used. Used blocks are the ones that the application has currently allocated. When an application frees a block, the allocator will try to coalesce that block with the other free blocks around it to reduce fragmentation. So if you have two blocks that are right next to each other and you free the first and you free the second one, they'll get merged into one bigger block, and then that will get freed. When you free a block, it goes onto the free list. There are 128 free lists. These are the doubly linked lists of blocks. Each of them is for a specific size. For example, the first free list is for blocks of size 8. The second one is for blocks of size 16, and so on. Free list 0 is special. It contains all blocks that are larger than 1024. I believe they're sorted by their size. In addition to, so if you're allocating some memory, if the application allocates 8 bytes, the heap allocator will go look into the free list for the 8-byte blocks, and it will just get that block, mark it as used, and return it to the application. If the free list is empty, then it will have to get a larger block and split off an 8-byte chunk. In addition to this standard free list management, we have the look-aside, which is very similar to the OLE cache that we discussed previously. The look-aside is a singly linked list for blocks of certain sizes. Again, you have look-asides. You have lists for, the first one is for blocks of size 8, the second one is for blocks of size 16, and so on. The thing about the look-asides is that they go through a much faster code path because there's no merging, there's no coalescing. So when you free an 8-byte block, it will first go into the look-aside list, unless that look-aside list is full. There's a maximum capacity for the list. And adding it to that singly linked list is much, much faster than going through the full doubly linked list, free list management. When you allocate an 8-byte block, first the heap allocator will look at the look-aside list, and if there's a block there, it will just return that. And again, that's a very fast operation. You just have to remove it from the linked list, and that's it. If the look-aside is empty, then it will have to go to the free list and perform the full operation. I've already described how the free algorithm works. Blocks that are larger than 512 bytes are not handled by the standard heap allocator. They get allocated directly with virtual. Oh, that's the free algorithm. Blocks larger than 512 get freed directly with virtual free. Blocks smaller than 1K get freed to the look-aside unless the look-aside is full. In that case, we would coalesce the block with the free blocks around it, and then we would add it to the appropriate free list. Oh, sorry. Shit. You should have told me that I was actually driving this without full screen. So the allocate algorithm works pretty much the same way, but in reverse. Large blocks larger than 512 get allocated directly from the kernel with virtual alloc. The smaller blocks get allocated from the look-aside if it's not empty. If it is empty, then we go and look at the free list. And finally, if we've used up all the memory and there are just no free blocks anywhere, we just get more memory for the heap using virtual alloc. So here are a few examples of how you actually use these techniques to manipulate the heap in specific ways. And